Hey, this is Horner. We're going to look at the next section and everything you need to know about rotational motion in order to pass the. And this section 4 is about moment of inertia. So before, when we talked about inertia, we just said it was the ability for something to resist motion. So if you have I don't know, you've got just a box, and if you push that box, you can feel force from it because you're changing that thing's inertia. So when we talk about moment of inertia, that's the same type of thing, but it's for things that are rotating. So for example, if you have a large bowling ball and if somebody rolls it towards you, it's kind of hard to stop. If you've ever tried to stop a bicycle wheel, if you pick up a bicycle and hold on to it and then spin the wheel with your hand, if you try to stop it, it's difficult to do because it's got what we call rotational inertia. So most objects, for most of the common objects at least, we can look up a formula for the moment of inertia. And that's pretty easy to do. For more complex objects, we can use this equation. And this is really simple. It's just the moment of inertia, which has a abbreviation of capital I, is equal to the mass times the radius squared of all the other parts. So if you remember inertia, we said in just regular old translational motion or linear motion is just really an object's mass. And anytime we need to convert that to rotational, we just take mass times, but instead of just doing radius, we're going to actually do the radius squared. Okay, so here are some common objects and their moments of inertia. And you'll notice that some of them are pretty easy, like a thin hoop or a ring of radius r and mass m is just mr squared. But if we make that ring really thick, then we have to end up doing this next equation. If I have a solid cylinder, I don't have to have all the stuff on the top, but I do have to divide by 2. So you'll see a lot of these get a little bit more complicated. On the AP Physics 1 test, though, what they will do is they will always give you what the equation is for the object and how it's moving. So that's really kind of a nice thing. Let's go ahead and try one. Here it says calculate the moment of inertia for a solid sphere with a mass of 10 kilograms and a radius of 0.2 meters. So to do this one, we're going to use the equation for the inertia of a moment of inertia of a solid sphere. So if you look on the previous page, you'll notice that for a solid sphere, that's I is equal to 2/5 times the mass times the radius squared. And you will always get the same units, which are going to be a kilogram times a meter squared. Notice that this one is different than a hollow sphere. So if you had a hollow sphere, this equation would be different. You do want to make sure you get the right object and the right equation that goes with it. So this is 2/5 times 10, which is our mass. And then our radius here is 0.2 meters squared. So if you do that math, you'll end up with 0.16 kilograms times a meter squared. For the next problem, this says find the moment of inertia of two 5-kilogram bowling balls joined together by a meter-long rod of negligible mass. That means that this rod doesn't have any mass. So we're really just worried about these two things that are spinning around the center of the rod. They want us to do that moment of inertia where you have two things on the rod and they're spinning about the center, and then they want you to do it where it's rotating around the 5-kilogram mass on this side. So that means that this thing is spinning in a circle kind of like that. This one is rotating in a circle like this. So let's try each one of these. For the first one, we're just going to say I is equal to the sum of mr squared. So this is going to be equal to, we've got to do the one on the left, so we'll just say this is mr squared for the one on the left plus mr squared for the one on the right. Mass on the left is 5, the radius here is 0.5, and we need to square it, plus 5 times 0.5 squared again, and you'll end up with 2.5 kilograms times a meter squared. For the one on the right, this one's going to have a little bit different moment of inertia, and it's because it's rotating about this center point. So you would think because there's two 5-kilogram masses here, that this moment of inertia would be bigger than this one. But let's check and see if that's true. So this is equal to the sum of the mass times the radius squared. And so for the first mass, we're going to have 5 times, and now our distance is 1 meter squared, plus 5 kilograms for this one, but there's no radius because we're spinning about its axis. So we're just spinning right on it. So we don't put anything on that one at all. And you could even say 0 squared if you wanted to. And here you're going to end up with 5 kilograms times a meter squared. So this one, even though we only have one of the balls that is really doing all the motion, because it's so far out, it actually has a higher moment of inertia than the two balls do, spinning about a half a meter axis. So anyway, big difference between the two, and you can kind of see that. For number 24, the next thing they want us to do is calculate the moment of inertia for a hollow sphere of mass 10 kilograms and a radius of 0.2 meters. So notice this one is a hollow sphere. So instead of 2/5, this one is 2/3 mr squared. So we'll go ahead and put in our numbers. 2/3 times our mass here is 10 kilograms. And our radius again is still 0.2 meters, so this would be 0.2 squared. So now we end up with 0.27 kilograms times a meter squared. For number 25, it says calculate the moment of inertia for a long, thin rod with a mass of 2 kilograms and a length of 1 meter rotating about its center of length. So when you look at the equations, you'll see that a long, thin rod rotating around its center of length. So that would be kind of like if I have, here's the picture of the rod, if it's rotating about this point right here. So it's going in a circle kind of like this. That's what it would look like. This one is going to be 1/12 times the mass, and instead of r, they might use length. So this would be length squared. So this is equal to 1/12, and then we have a 2 kilogram rod. We know that it is 1 meter, and that is squared. So we're going to end up here with 0.17 kilograms times a meter squared. So pretty easy problem. You just have to make sure that you kind of know what it's doing. The next one's a little different than this one is, because instead of rotating about the center, now this rod is rotating about its end. So now we've got the same rod that we had before, but this time it's rotating right here, which means it's making a great big circle as it goes around. So this one is I is equal to, and this one's 1/3 ml squared, and that's equal to 1/3 times 2 times 1 squared, and so we end up with a much higher moment of inertia, 0.67 kilograms times a meter squared. Next question is a good thinking question here. It says an object with uniform mass density is rotated about its axle, which may be in position A, B, C, or D. They want you to rank the object's moment of inertia from smallest to largest based on axle position. So we know that if it's pretty equal on both sides, it probably has the smallest moment of inertia. So if we rotate it about C, you'll notice that we don't have a lot of length on this side or on this side, and the two sides are pretty even in terms of their weight or their mass. So the smallest would be letter C. The next biggest would then be the one that's just a little bit further from the center, so that's letter B. For the next one, we want the next point that's a little bit further from the center, and that would be letter D. And then finally, the one that it is the furthest out, and that would be letter A. So if you had to explain this, we would say I is equal to mr squared. And notice that if we're right at the center, that makes it a little, that makes this, essentially makes this 0. If we move a little bit further out, we still have the same mass, but now we've got r squared for the distance here. Then we have the distance here, and then finally we have this bigger distance. So that is your reasoning for number 27. For the next part, this one is about Newton's second law for rotation. So when we thought about dynamics, we learned that forces do cause objects to accelerate. The bigger the force, the bigger the speed that it has, and the bigger the mass, the smaller the translational acceleration. So that's our equation. When we do this with something that is turning, instead of talking about force, we're going to talk about torque. And torque is really just equal to the moment of inertia, which we just learned about, times the angular acceleration, which we learned about earlier. So let's go ahead and try this. It says, what is the angular acceleration experienced by a uniform solid disk of mass 2 kilograms and radius zero point 0.1 meters when the torque is 10 Newton meters is applied? They want us to assume that the disk spins about its center. So here we're going to say that the net torque is equal to the moment of inertia times the angular acceleration, where the moment of inertia, and this is for a uniform solid disk. If you look at your equations, you'll see that's 1/2 mr squared. And then we multiply that times alpha. So remember, I is this equation for this object, and then alpha is our angular acceleration. If I want to know what the angular acceleration is, I need to solve for that. So the angular acceleration here is going to, we can kind of ignore this guy right now. So the angular acceleration is equal to, we need to multiply both sides by 2, so that'd be 2 times the net torque, all divided by, and then we're going to put mr squared on the bottom. So here we have 2 times 10 was our torque, divided by our mass, which was 2, times our radius, which is 0.1, and we have to square that. And when you're done, you'll end up with 1,000. And then remember, it's angular acceleration, so this one's going to be in radians per second squared. That one's number 28. Let's go ahead and take a look at the next one. Roundabout, this is a merry-go-round, a roundabout on a playground with a moment of inertia 100 kilogram meter per second squared. I'm sorry, kilogram times meter per second times a meter squared, kilogram times a meter squared, starts at rest and is accelerated by a force of 150 newtons at a radius of 1 meter from the center. If this force is applied at an angle of 90 degrees from the line of action for about 0.5 seconds, what is the final rotational velocity of that roundabout? So the very first thing that we probably need to do is go through and think about all the things that they've given us. And one of the things that they gave us was the moment of inertia. So we know I is equal to 100 kilograms times a meter squared. We know that the force that they gave us is 150 newtons, and we know that that force is at 90 degrees. And all that means is it's the full force is going to be exerted on that. We also know that the time for the rotation is about 0.5 seconds, okay? Well, actually, it's not the time for the rotation. That's the time for the force to act. So let's go through, and we also know that the original angular speed is equal to 0. We want to find out what is the final angular speed, but in order to do that, so we want the final angular speed is equal to the original angular speed plus alpha, which is the acceleration, times time. We have this thing we know, which is 0, okay, plus we know the time is 0.5, but we have a problem. And the problem here is we need to figure out what is this acceleration. So let's go back. Did they give us anything else? Yeah, they gave us moment of inertia. So let's figure out what is the torque on this thing. Or better yet, did they give us torque? Well, they didn't really give us torque, but maybe they gave us something close to torque. We know that torque is equal to two things. We said it was equal to I alpha, but remember, torque from earlier is also equal to the force times the radius times the sine of the angle. So here's what we're going to do. Let's go ahead and let's solve this equation for alpha. So alpha is equal to the torque all over I. But we said right here that the torque is equal to the force times the radius times the sine of the angle. And then we're going to divide it by the moment of inertia. Since they gave us that number, we don't have to do any more with it. So let's plug everything in. The force is 150. We know that the distance that the force is applied at is 1 meter. And then we're going to do the sine of 90. And we said that that's just equal to 1, so we don't have to worry about it. And we divide by that 100 kilograms times a meter squared. So when I'm done, I'm going to end up with 1.5 radians per second squared. And that is my acceleration that I'm going to put in here. So now I put 1.5 into this spot, and I do my math, and I end up with 0.75 radians per second. And that would be my angular speed, my final angular speed. So it started at 0 and it sped up in that little tiny time to 0.75 radians per second. Let's go ahead and take a look at the next one. This is number 30, and it says a top. So they're talking about a kid's top, so a little toy top, has a moment of inertia of 0.001 kilograms times a meter squared, and it's spun on a table by applying a torque of 0.101 newton times a meter for 2 seconds. It's if the top starts from rest, find the angular velocity of the top. So this one we know that the net torque is equal to I times alpha. So we said that if we want the acceleration, we just take the torque and divide it by the moment of inertia. They already told us the torque, and they also told us what the moment of inertia is. So if I divide the two, I'm going to end up with 10 radians per, and remember it's acceleration, so this is going to be seconds squared. Now we're just going to use our kinematics equation we used earlier. So the final speed is equal to the original speed plus the acceleration times time. So this is equal to 0 plus 10 radians per second squared times our time, and they told us that it was 2 seconds. So we're going to put in 2 seconds, and we find out that our final angular speed is 20 radians every second.